Okay, so let's take a look at the second exercise. And the same thing as earlier, when you have the second exercise, you first make your own copy. There we have the own copy of the exercise, and basically then start filling it. The first three questions I think we will be doing together, since that takes a lot of time. Usually this is, I give 1 week for students to do this exercise by, but on the other hand, you need to start applying these filters, not just learning the deep parts of this pool. You need to basically start learning how to do the filters, how to design the filters. That's more important. Okay, this is important if you have a black box and you want to analyze what is inside the black box. Okay, for system evaluation, yes, but for designing a new, not that important. Okay, so now I have that one open. Okay, and are you already running the MATLAB? No. Yes, okay. Try to make it running for tomorrow, then we can switch over. But now let's go back to the Octave. I start from the scratch again, not to be confused with the previous exercises. The first exercise is about linearity of the systems. Okay, let me just test the first one. Since there is a function, let's make a function. How to make function in Octave? For example, like this. myfunc.m. Create. All right, that's the function. If you start typing, on command window, you say edit and then the function name, it basically makes you a nice prototype of the function there, and you don't need to start from totally scratch. Okay, basically it has this area with continuous the comment lines. When you type help myfunc, it'll actually shows the beginning of that file. All right, so basically we can, okay, function, let's see, where does it go? It also gives nicely the author and when it was created. Let me change this a little bit. So my first function actually is same as in here. Let's copy that one in here. Percent sign. I prefer percent sign as the starting of the comment. So my function, it's basically defined so that I have only one input. Okay, no two inputs needed, and it basically just adds number 2 to my input. Simple function. And I can then go to the command window and just call it myfunc. If I give it one number here, number 2, then it returns 4. Or if I give it a vector 1, 2, basically it gives my 3 and 4. So basically it just returns. It does for the data whatever I'm asking it to do. Now let's test if that system, my func is linear. Linearity means if and only if the let's see, function at okay, let me see, can I copy that one? So that's the linearity requirement. Yeah. Wow. That was fun. Wow. The copy paste seems to be a little bit tricky here. Delete that. No, it doesn't delete. Okay. Let me write it again. It's linear if and only if my function, when I give it a scaled input, oops, a times x1, add it with another scaled input, it would be the same as this scaling product goes out, and then we have the first input and plus. So this basically is the same thing as testing if the superposition actually is okay. There. So only if that is true, the equality there is true, then the system is linear. And for that sense, we take a couple of random sequences, random numbers for testing. So this must be true for everything. One way of testing is the engineering way, brute force, with random numbers. It works 99% of the cases, and that's enough. That's engineering accuracy. If you need more accurate results, then you put more numbers, calculate more. Okay, this is not mathematical proof. This is engineering proof that this system is linear or is not linear. I don't know it yet. So random numbers for testing. I take A, for example, one random number. That looks like pretty random. And B is also one random number. Different. You probably got the same numbers if you started from scratch. If you didn't, then you get some other numbers. You can actually also give a seed number for the random number generator. But for good reasons, when you start either Octave or MATLAB, it actually starts always from the same random numbers. Pseudo random numbers. No, but you can randomize it by, for example, starting with the seed number which is tied into your clock. Then it's more random. Makes sense, right? Okay, x1 is then more random numbers. For example, 100 random numbers. It doesn't really matter. But anyways, 2 vectors. So those are inputs, x1 and x2. And then we have the scaling factors a and b. And now I have quite a lot of linearly independent values to use as random numbers, to randomize this whole thing. And first I calculate the left-hand side, which is basically the output for the weighted sum. FA x1 B x2 equals to my func with A times x1 plus b times x2. So that is the system output for weighted input. Then I calculate AFX1 plus BFX2. The right hand side. Should I actually write it? Oh, well, it is 8 times my func x1 plus b times my func x2. Okay, as you can see, this is really brute force, and it's not more than that. You just test if the weighted inputs will produce the same as the weighted outputs, separately fed signals. Now I have two vectors, output vectors. How to actually check if those are same? Any suggestions? How to find if the vectors are the same? When the vectors are the same? When the distance is 0. What is distance? This is multidimensional vector. What is then the distance? Well, it's the second norm of the difference. So difference of those vectors actually would give so basically we calculate the difference, DFF equals FAX1 BX2 minus AFX1 BFX2. Like that, maybe. Who came up with those names? Variable names. I did. Okay, so this is the difference vector. And this actually must be 0, meaning the norm of it is 0. We test if this is 0 or not. It's not even close to 0, which means that this system is not linear. When you add just a constant number to your input, it's not linear anymore. System does not operate linearly. That was non-zero. System is not linear. Okay. Good. Any questions? The correct answer for this one actually it would be, let's see. Adding the MATLAB commands actually, if you were doing this yourself and wanted to give a perfect answer, you would take these commands like that, Control C, and add those values here, and then make a, since there is that function that I don't necessarily know unless you give it to me, I'll take this this my func here and transfer it here. Oops. Share it. Anyone with the link can view. Done. And then on that copy, you basically can add the link. Why I didn't? Of course, I didn't get the link. Get shareable link. All right. There we go. Apply. Okay, that would be perfect answer. Meaning the copy paste of the test with the answer, maybe block letters, and then link to your function. Otherwise, I don't know your function. Okay, good. But that was just the first part. First part, checking if those functions are linear or not. Okay, you don't need to work on these three other ones. I can already give you that. This is not linear when you put it power of something. This is linear and this is linear. So basically, first two systems are not linear, but the rest of those systems are. Okay, but basically linearity check is very simple. You just check if basically this is true. All right, causality. Causality basically means that you must actually first generate some index vector which also have negative indexes, and then start a signal at some point and see if it produces also values for these negative indexes. So it cannot. So basically, all of that must happen after the signal starts, not before. And to test it, I can use the previous. Just a moment. Causality. Testing for causality. So basically we start a signal, an input signal at n equals to 0 and check if output has signal before that. Okay, this is kind of when you have a real system, of course, it does not give you anything on output. Otherwise, you start first figuring out why it's giving output for no input. Okay, but anyways, this is, well, this exercise is to understand the causality. So we can actually take that index from minus 49 to 50. And then take the x3, for example, so that it's x1 dot times or x1 dot times double of n greater than equal to 0. So basically we are using the unit step to start the signal. And it looks like this: stem n x3. That's the input. So it doesn't have anything happening until you go to the time 0. Okay, then we will see what happens on my function for this one. So we take just the let's see, y2 equals my func h3, and we test for the negative index values only. So we calculate the norm of y2 on the points when n is less than 0. Okay. That's one way of checking this, which points to choose. So this one gives me true-false vector with the same size as that one. So this together actually gives the those values of y2 where the index is less than 0. So we are looking only on, wait a minute, do I have the graphics window here somewhere? No, I don't have it anymore. Oops, there. Wait a minute, this is not correct. Why did it give me that? It's supposed to give me 0. Huh. What? Yes, of course. It's not causal. I almost went into this. Yeah, okay. So the system is not actually causal, since it has a constant output even before the input happens. Okay, so it's not causal either. And basically the test was this numerical testing, so this what was correct. So this is non-zero. Yeah. Even without any action, there was reaction. That's a constant. All right. And there I could also see causality. Testing for causality, Control C, and then I can copy that. Oops, here. So that's, oops, not non-causal. But okay, so next part. Time shift invariance. We delay the signal. Use the same signal, but we delay it a little bit and then see if the output is exactly the same except for the delay part. So that's, oops, the test actually is something like that. Time shift invariance test is simply see if the delayed output corresponds to delayed input. So basically, we first make the delay. Okay, how to make the delay on this for any system. So basically the delay is we can use command filter to do the delay. So this is one time step delay. It basically uses convolution to calculate it. But anyways, we have the, for example, that x or 3 there as a test vector. It's just as good as any. We take the delayed x3 is filter 0, 0, 1, 1, x3. So this is the delaying input, and we can calculate then the delayed basically the output based on that one. Delayed output is same as my func dx3. Then we calculate just the output 3 with my func x3. So this is without delay. And we actually delay this one. So it's just a matter of where the delay is. Is it if it's before the input or after the input or after the output? Okay. And basically now we have the delayed output. Okay. And now we test if these two things are the same. Hi. And only way we can we know how to do it is with calculating the norm of the difference. y3d minus dy3. Answer is 2. Now the question is, how come it has different value? Okay. This is something we need to basically take care of by hand, because we made an artifact. I will show you what I mean about that. So let's let's take a look at y3d. First few values. Where did that 0 come from? To the beginning of that. That's the artifact what we did ourselves. We delayed the output, and since we didn't have any other information, we added 0 to the beginning of the data. So this test actually works only if we take the first or delayed number of the values out from the beginning of the data. Otherwise, you corrupt this test by adding that extra 0, which was not the behavior of the function. It was something you did yourself. Okay, and now we have the value, the difference is 0, which means that this system is time shift invariant. Yoo-hoo! So what? Let me copy that one there. So this one was time shift invariant. Because practically this here is 0. Not the original, because basically we added something by delaying the signal ourselves. Guess that this we needed some additional values there on the beginning when we shifted the data. All right. There we go. So those are the 3 questions. Okay. The next one. This is a nice exercise. I will let you to do work on that yourself. I will just give you some hints how to do this. Oh, well, I have this one. What you need to do in this the signal flow chart, you need to follow the signal and determine what is the difference equation. So you're looking for yn from this information, meaning that if you have a situation like that, well, either z minus 1 or d, when you start with the x of n, here you have x of n minus 1, which is delayed again. So this is xn minus 2. This here, the signal is just simply b0 times x of n. Here we have b1 times x of n minus 1, and so on. Same thing for the output. You have, in this point, you have y n minus 1. After that point, you have a1 times y n minus 1, and so on. And then you just basically calculate from here to see what comes out from here, which is the y of n. This is paper and pen exercise at the beginning, which gives you the difference equation. Okay. The next part, system coefficient A and B. This is the place where most of the mistakes are done on this course. Okay. Draw it on the top. So if you have this difference equation compared to this one, the sign on the right hand side is minus. So on the right hand side, okay, let's go from 1 to n. So this is the feedback term. When you figure out your transfer function, or not the transfer function, difference equation on this form, that yn equals something, then you need to basically change it so that you have the sum of some the weighted output values equals the sum of the weighted input values. You need to make sure that when you move these parameters on the left-hand side, you also change the sign. And those are the coefficients for the system. So on the left-hand side, we have A1, no, not A1, A0, which is always 1. Okay, 1 times. So that is basically A1, A2, and so on. And on the right-hand side, actually, let's put it here. So here we have the vector is actually the vector A0, A1, AN, as many as those are, and on right-hand side, the B vector B is B0, B1, Bn. There. So always with the corresponding with the delay value that defines the place on this coefficient matrix or coefficient vector. Okay. Another mistake you can easily make is that really this is due to history. From the history of digital signal processing, these coefficients are always have been marked A coefficients for Y and B coefficients for X in that order. But the MATLAB actually, when you call the functions, it's the opposite way. But you need to figure out that one. Okay. When you have those coefficients, then basically you need to calculate the zeros and poles and determine if the system is stable. And then basically do the A and B's for the following system, zeros and poles, or else sound sample and comparing input and output. Wow, this is a lot of fun. Let me show some parts of it. Something about there. I will start from difference equation. If the difference equation is given, y of n equals, for example, x of n plus 1.5 times x of n minus 1 plus 0.4 times, just to make it interesting, n minus 2. I have no idea what kind of system this will be. And then more parameters. So, for example, 0.5 times y of n minus 1 plus 0.25. Let's make this one minus 0.2 times y of n minus 2. Okay. So if the system coefficients are like that, then basically what you need to do in your mind change these two coefficients on the other side and also change the sign. Don't change the equation, change the sign correspondingly. And then basically equal to the rest. Now it's quite straightforward to define what are the B's and A's. So A, the first is the multiplying factor for y of n. Second one is for the first order delay, and then third one is for the second order delay. Okay, these are the A's. Similarly, B's equal 1, 1.5, 0.4. So corresponding terms, nothing more. Oops. Wait a minute, I can actually do it the fancy way. Oops. Who cares? I do. So you just pick the corresponding terms from the difference equation, and that's it. Now we can use these coefficients, for example, to calculate the zeros and poles, which is done by command zplane BBAA. Okay, those are the zeros and poles. And this is stable system because of the zeros can be anywhere, and the poles are both within, inside of the unit circle. Simple. We can see that this is a stable system. Good. We can calculate these zeros separately by saying ZZ equals roots BB. So those are the coordinates for the zeros of the system, and poles are roots of AA. So these are poles. Yeah, complex conjugate pair. Good. What else we can do? Let's see what is required here. System coefficients we've done. Zeros and poles. And stability, yes. Then we can actually, let me see, start filtering. So these are actually filter coefficients. Any linear time invariant system can be considered as a filter of some sort. So this is the system. That's a filter. We can calculate, for example, the filtered output of for signal X3. There. So filter command actually takes these coefficients as they are, B's and A's, like that, and that's the output for any input. And then we can actually also plot it. Let's see, how can I do it? Easiest way, stem NN X3 was my input. Where did it go? There it is. Okay, that's my input signal, and then I can actually say hold on and stem FY3 on the same, but using red markers. Does it work like that? Yes, it does. Okay. And there's the comparison. So what did my system do for the signal? Definitely it did something. It seems that it actually, at least it amplified the signal. It may actually enhance a bit of the higher frequency components, maybe. But that's basically the further analysis for the system behavior would be for tomorrow. Your example is, let's see which system. This system here. It's weighted average filter. Not uniform weighted, but it has some sort of other shape here, envelope. It has a kind of different envelope, not a uniform values, but a little bit on the edges, both edges. It has some weighting factors there, but still, I would expect to have a some smoothing kind of operation from that system. And when basically you do the sound sample, okay, and compare the original the sound sample with filtered sound sample, meaning using that as a filter. So this is your filter. And then comparing the values. Okay, another thing actually, on the first exercise there was the signal to noise ratio was given. Now I have given directly the sound amplitude, meaning the scaling factor for the random noise. Amplitude means the same thing as in sinusoid. You just multiply the sinusoid with this amplitude. For the random noise, same thing. If you have this random noise with a variance of 1, then basically you can just multiply it with that amplitude. Okay, good. That was fun, was it? Yeah, everybody's smiling. Smiling with me or at me. Okay, good. But anyway, so yeah, so that was more or less everything what I wanted to show you today. You still have some time to work on the second exercise. The second exercise deadline would be tomorrow, I think. Let's see. The first exercise deadline is today, but I think I have the second exercise deadline tomorrow. So I try to push this so that, yeah, October 5. Yes. And you can work on that one either during this evening and next night and early morning. Then sleep a couple of hours and be here at 10 a.m. again, sharp 10 a.m. tomorrow. And then basically, I will start a new topic tomorrow. So if you want to really get a good grip on this course, you might want to work on this one tonight instead of going to bed.